To Colloquium. We're super happy to have Guha Thakurta with us today, and the topic is resolved stellar populations. And Raja is a world expert on this topic. He got a PhD in 1989 from Princeton. He was department chair at the UC Santa Cruz until this year. He's got over 300 refereed publications and about 25,000 citations. He's got huge, not huge, there's a very steady pipeline of really talented students that he has supervised as well. So he's really an influencer in astronomy. And he's got a passion for outreach. So he loves he loves spending his energy broadening, bringing the joy of astronomy to students of all ages and also to the public. He's in various programs. There's an equity for STEAM program. STEAM is science, technology, engineering, mathematics, and art. I think I got that out of order. And he's in the Shadow of the Scientists program and Python and research and science internship program. And he is also an artist, and you can look him up on on the web and find that he does portraits. He uses mostly oils and pencil, but he also does wood carvings and paints ceramics and glass. Wow. So today's talk, though, science talk, and it's on galaxies inside and out. So thank you for joining us today. And maybe we should welcome him.
Thank you very much, Guy. And do you want me to, can I start my talk now?
Yes, you can go.
Okay, I'm going to go ahead with this. Okay, so I just returned from Hawaii a couple of nights ago, where I was studying this very galaxy. And I was in Hawaii to use the Keck telescope. So I want to show you a picture of the Keck telescopes. This is a photograph taken by Laurie Hatch, a former resident of Lick Observatory, Mount Hamilton. She was a very talented photographer. This is a Mauna Kea sunset superposed on one of my favorite galaxies in the whole world, Andromeda. And so I'm going to talk about how we use these telescopes and other telescopes to study resolved stellar populations in those three galaxies: the Milky Way, Andromeda, and Triangulum. Andromeda is M31 and Triangulum is M33. If there's time at the end, perhaps during the Q&A session, please feel free to ask about the outreach that Guy so kindly mentioned. Guy, thank you for that wonderful introduction. Thank you, really appreciate it. So please ask me about that. Many of you are observers and use telescopes to do your research. My colleague from Shadow of the Scientists, Jamaica Marshall, is actually on this Zoom call, and she and I would be happy to say a few words about how you could get involved in these programs to really increase access to the work we do, and more generally increase access to critical thinking, of which there's a serious need around the world, especially among youth. Okay, so I'm an observer, but I thought I would do a little simulation of galaxy formation, bottom-up simulation of galaxy formation. Galaxies form small, and then they come together to form bigger and bigger galaxies. In fact, this snapshot that you see on the screen is from a computer simulation, somebody else's computer simulation. But here's my own computer simulation of bottom-up galaxy formation. This is how the Milky Way formed, bottom-up, just like that. So I'm going to talk about the Milky Way through the lens of those three surveys: HALO7D, BP3M, NGVS. This is going to be acronym city. I'm also going to talk about companions of the Milky Way, three companions actually, not just two, three companions, M32 plus minus 1. So M31, M32, and M33. And those are through 5 different surveys: SPLASH, TREX, PHAT, PHAST, PHATTER, HST promo. Don't worry about the acronyms. I'll get into them in a little bit. There won't be much time for this, but I have 1 or 2 slides to talk about nearby galaxy groups, nearby groups of galaxies. These are Milky Way analogs, but they are located somewhat further away than the local group. So these are a few megaparsecs away, as opposed to the 1 megaparsec, rough 1 megaparsec size of the local group. And this will be through the lens of the Pisces survey. I just have 1 slide or 2 slides on this. Okay, so I'm going to start with the Milky Way and the accretion history of the Milky Way stellar halo. This is something that I'm really excited about, the HALO7D survey. And it is really a 2-part survey. We're actually expanding to a 3rd part, but that's related to the first of the parts. So the first part is using Hubble HST archival data, archival imaging in particular, deep archival imaging, to measure proper motions of stars. So this is deep multi-epoch HST imaging. Very well known to extragalactic astronomers. Candles fields were where we started. Candles is a multi-cycle treasury program that Sandy Faber led. And this was a program to take 4, actually more than 4 fields in the sky, but I think it was 5 fields, but 4 of them have deep multi-epoch HST imaging. Multi-epoch, 2 epochs of HST imaging separated by, say, 5 years or even 10 years in some cases. And what we used in these images is we used the background galaxies, the distant background galaxies, as the cosmic wallpaper against which to measure the proper motion, the lateral motion of foreground Milky Way stars. So we measured proper motions for about 1,000 main sequence turnoff stars in the Milky Way halo. I say remote halo, but not terribly remote, maybe 25 kiloparsecs from us. So 3 times the distance of the solar system from the center of the Milky Way, roughly that distance. 20 to 30 kiloparsecs was a typical distance of stars. And I just want to emphasize that this wallpaper is super important. This proper motion of stars, even with a 10-year time baseline, is very subtle. Stars move by fractions of a pixel. Our positional accuracy, this is when I say our, there's a big group of people based at Space Telescope mostly, who really perfected the art of measuring the positions of stars super precisely, taking account of charge transfer efficiency effects. This is the genius of Jay Anderson for the most part, but there's a team of people surrounding him, Roland van der Marel, Tony Sohn, Mark Fardell. We've been fortunate to be, our UCSC group has been fortunate to be part of this. Their accuracy for measurements of the positions of stars is well under 1/100th of a pixel, down close to 1,000th of a pixel. And so even if stars move by a fraction of a pixel, they can measure it super precisely with very high significance. They can measure these. Now, this is like trying to watch a very slow-moving insect move across the wall of the auditorium where the in-person audience is seated. Right? If you're trying to watch the motion of a very slow-moving insect, by taking images that are very far apart in time, it helps if that wall has intricate and highly patterned wallpaper. And this background of galaxies that you see on this slide is that background of cosmic wallpaper that we use. Okay. Now, in addition to these Hubble measurements, we have a very deep Keck spectroscopic program. Now, the HALO7D observations have all been taken. We are now extending the survey to other lines of sight, but we have between 8 to 32-hour integrations on the Keck 10-meter telescope of something like 1/4 of these stars for which we're measuring proper motion. Some of them are just too faint for us to get spectra. And also, we get spectra of something like 1,500 galaxies. We have obtained spectra of something like 1,500 galaxies. Now, this combination, deep HST, multi-epoch imaging, and very deep Keck spectroscopy, makes up the core of the HALO7D survey. HALO7D stands for Halo Assembly and Lambda CDM. observations in 7 dimensions. The 7 dimensions are position of the star, 3-dimensional position. We have a rough line of sight distance for each star. We have sky position. So we have, from that, we have 3 dimensions of position. From the proper motion, distance, and radial velocity, we have 3 dimensions of velocity. And the 7th dimension is chemical composition. It's really a complicated dimension because we are measuring more than one number for chemical abundances. We're measuring 2 numbers, Fe over H and alpha over Fe for these stars. We used the four of the candles fields, but there's a 5th line of sight, which is the foreground of the Andromeda galaxy. We studied stars in the foreground of Andromeda. And there are 3 papers published by Emily Cunningham, a PhD student at Santa Cruz, that really form the backbone of the HALO7D survey, the galactic component of it, the Milky Way component of it. There is a series of papers about the distant galaxies, and those have been led by others in the group. And the names you see at the bottom, first row of names are people who've been involved in the Milky Way component of the survey. The second row of names are those who've been involved in the distant galaxy component of the survey. And you'll see some familiar names, and Faber and Koo. They were the faculty leads, and Charlie Conroy, when he was faculty at UC Santa Cruz. The 3 of them were the faculty leads. The other 3 names are junior people. Same thing for the galactic component. The junior people whose names I've highlighted by underlining have done most of the work. Okay, there's Emily. This is part of her PhD thesis from UC Santa Cruz. She graduated in 2019. She's a postdoc. She was a postdoc at the Flatiron Institute, is now a postdoc at Columbia University. She's applying for jobs, faculty jobs this year. And Alice Deason, who was a postdoc at the time at UC Santa Cruz when we started HALO7D, working with Connie and myself. Alice is on the faculty at the University of Durham in the UK. All right. And I assume we'll take questions at the end, so I won't pause for questions. I'm going to move on to just describing a few highlights from HALO7D before I talk about a different aspect of the Milky Way halo. So this is a plot from one of Emily's papers on HALO7D. And what you see in the different panels are different measurables, different things we can measure for these 4 lines of sight in candles. I haven't shown the Andromeda foreground here, just the 4 lines of sight. You see the lines of sight named in the lower right panel. EGS is the extended growth strip, Goods South, Goods North, and the Cosmos field. These, as I said, these are magnet fields for distant galaxy surveys. But what you're seeing here are foreground stars, Milky Way stars, in these 4 fields. And the color coding, blue, orange, green, and red, apply to all panels here. Upper left panel, you're seeing the mean rotational motion of the halo. Then you're seeing the dispersion, and the second, in the middle, top middle panel, you're seeing dispersion of the radial component of the velocity, radial relative to the galactic center. Distances, a cumulative distribution function for distances in kiloparsecs, and you can see that, a typical distance is 20 to 20-ish kiloparsecs. It's a logarithmic x-axis there. And the dispersion in the tangential direction, that's sigma phi. Sigma theta is polar motion. And again, the thing, and then the anisotropy parameter in the lower right, beta. This is the ratio of energy in tangential motion to radial motion. I think I might have had that reversed, but what you see here, the main thing to note, it's not a surprise at all, is the 4 different fields of view have different characteristics. If you poke pencil beams through the halo is not well mixed. And this is obviously not a surprise. We've seen that the Milky Way is made up of the partly digested remains of the satellites it has cannibalized, the halo. And yes, the energy in the tangential component is in the numerator of beta, and the radial component is in the denominator. So indeed, if it's a purely radial orbit, you get beta of 1 because the numerator of that equation is 0 if all the energy is in the radial component. And then if all the energy is in the transverse component, then you get a value of minus infinity. So beta is not a symmetric parameter. It runs from minus infinity to 1. And 0 means isotropic. There's equal energy in the tangential versus radial component. So isotropic velocities. Okay, that's from, that last one is from Emily's thesis. This is a published paper. It shouldn't say 2022 in prep. It's a 2023 paper that Kevin McKinnon published about the abundances of stars. And again, you see inhomogeneity in the average properties of the different lines of sight. And this is Kevin McKinnon. He is no longer a PhD student. As of 2 weeks ago, he's completed his PhD, and he's going to start a postdoc at CETA in the beginning of the year. Kevin was co-supervised by Connie Rockesy and me. And then another PhD student, Miranda Apfel, is working on this paper. It's not submitted for publication yet. That should say 2023 in prep. And it's taking these 4 lines of sight in HALO7D and running them across 2 different, in this particular case, 2 different Bullock and Johnston simulated halos. Now, she's done this for all 11 Bullock and Johnston simulated halos. This illustration just shows 2 of them. And I want to explain this graph in a little bit of detail. There's a lot of information on this slide. In the far left are these panels that Bullock and Johnston provided, where they describe the accretion history of the halo. If you can see my cursor, this panel up here is 1 halo. This row up here represents 1 halo. And this a simulated halo, where galaxies are cannibalized to produce the halo. The lower panel is a second halo. And the main difference between them is really in the y-axis of these plots with black dots. Every black dot represents an accretion event. The size of the black dot tells you how big the satellite was that got cannibalized. So small dots are small satellites, large dots are relatively large satellites. But the y-axis is the time since accretion. So you can see that in this upper halo, there's been no significant accretion for the last half of cosmic time. All the accretion events happened 8 or more gigayears ago. The X's, if you look closely, there are X's. These are intact satellites. These have not yet been disrupted. So the X's are satellites that are that were acquired but haven't been disrupted. That's what the X's mean. The filled circles mean these satellites have been partly or completely disrupted. Now, so the lower simulation shows you an example of an accretion history of a Milky Way sized galaxy where there has been, some amount of accretion, these dots down here, some amount of accretion in the last half of cosmic time, 6.5 gigayears ago. And what the x-axis is the orbital circularity. So 1 means it's a circular orbit, 0 means it's a radial orbit. So these are the 2 parameters they use to describe the simulated halos. And in particular, the lower halo, because it's had more recent accretion, you expect it to be more structured than the upper halo, which has had more time to virialize, to dynamically mix since its last significant accretion event. And you can't really see that from these maps, these 3D representations. In both of them, you see substructure. But if you run these 4 HALO7D lines of sight through these projected halos, we rotate them through the halo, what you can see is these cumulative distributions of velocity, VGSR, is very tight across the 4 fields, across the 4 HALO7D lines of sight, whereas there's more variation in the lower halo. This is saying that even with 4 lines of sight and limited numbers of stars in each line of sight, you can start to say something meaningful about the accretion history of the Milky Way halo. And so this is something that Miranda is exploring with all 11 halos, not just with these 4 lines of sight. She's talking about 30 lines of sight because that's what we're in the process of extending the HALO7D survey to, 30 lines of sight. Even that is small, of course, compared to all sky surveys with very small numbers of stars, but 30 lines of sight with detailed information can really start to pin down the accretion history of the Milky Way. That's really what Miranda has been working on. She's a PhD student at UCSC, again, working with Connie Rockesy and me. Okay, I want to move forward to a different aspect of the Milky Way. And I'm sorry, I'm not pausing for questions here, but I will afterwards. I want to say a little bit about the extent and kinematics of the Milky Way stellar halo. I talked about the HALO7D survey, which goes out to 20-ish kiloparsecs. I'm now going to go out 10 times further than that. We're going to talk about distant RR Lyrae as discovered in the next generation Virgo cluster survey and in other time domain surveys. So my particular connection to this work is through my PhD student and collaborator, Eric Peng and Yuting Feng, whose names are on that paper you see listed at the bottom. Yuting Feng is a PhD student at Santa Cruz, and he's searching for distant Milky Way halo RR Lyrae stars in the next generation Virgo cluster dataset. So NGVS stands for that, Next Generation Virgo Cluster Survey. It was a CFHT MegaCam imaging survey of the Virgo cluster, 104 square degrees in 4 filters, UGIZ, using MegaCam. MegaCam is a 1-degree imager, but there were 104 different pointings. And the way the data were acquired for purposes of flat fielding to really average over temporal variations in the atmospheric air glow and how that varies across 1 degree, so that we could study real low surface brightness structures in the Virgo cluster. Because of that, the way the imaging was done is we didn't just pound away at one of these 104 fields, finish it, and then go on to the next field. Instead, we took some imaging in some filters, in each filter in a field, then we moved on to other fields and imaged them before we came back to that first field, so that we built in a time gap so that if there was any variation in the Earth's air glow, just the atmosphere and its brightness change over 1 degree, we allowed for that to happen, allowed to average over that. So the data were collected over a period of years, actually, for a given field. And that, of course, opens it up to time domain surveys. And this is the first paper to explore the time domain aspect of NGVS. And we've used it to find foreground, by foreground, I mean in the foreground of the Virgo cluster, Milky Way halo RR Lyrae. We found the most distant RR Lyrae known in the Milky Way, beyond 300 kiloparsecs. So that is 40% of the distance to Andromeda. We're not looking in the direction of Andromeda. We're looking in the direction of the galactic pole, roughly speaking, the galactic North Pole. But other surveys are finding stars at comparable distances out to 300 kpc. And I just want to emphasize that 300 kiloparsecs is about 40% of the distance to the Andromeda galaxy. Andromeda, we know, has a comparable size halo. So this really starts to break down the notion of island universes that Immanuel Kant talked about in the 1750s, I guess. 1755 is when the whole concept of island universes was popularized by Kant. So the sizes of galaxies, especially the outskirts, if you take the remote halo into account, the sizes of galaxies is comparable to the distances between neighboring galaxies. Here are some of the RR Lyrae that Yuting has found in NGVS. These are 2 RR Lyrae. The one in the upper left is an example of an RRAB star, the very asymmetric light curve. And what you're seeing on the x-axis is the phase. So these are phase-folded light curves. We look at the variation fit for a period, and what you're looking at is where in that cycle, where phase 0 is defined to be the brightest point in the light curve, where in that cycle our measurement point lands. The curves are empirical RR Lyrae light curves in these same filters, UGIZ, from the Sloan Digital Sky Survey Southern Stripe 82, I guess, from the Southern Stripe. And so they're very well sampled light curves for about 500 RR Lyrae. And we find the kind of RR Lyrae light curve, the shape that best matches. We fit for an amplitude, constrained fit for the amplitude, because the amplitudes tend to be higher in U and G than in I and Z. So it's a constrained fit. And what you see in the lower right is an example of an RRC, somewhat more symmetric, closer to sinusoidal light curve variations. Again, you see the same pattern that the U band tends to have the highest amplitude, and the longer wavelengths, the G and I, the I and Z tend to have smaller amplitudes. So if we take these and we compare them, so Uting has found about 200 RR Lyrae, about a third of them, so more than a third of them, 84 of these RR Lyrae were already known. The bright ones were already known through the Pan-STARRS-1 survey. And Pan-STARRS-1 measured periods. We've measured periods, and what you're seeing here is a comparison of those periods. So most of the stars lie on the 1-to-1 line. That's this line here. Red are RRCs, blue are RRABs, and the dashed lines are sort of the aliasing lines. So, of course, these are ground-based measurements, whether it's PS1 or NGVS, and the star has some intrinsic period, but there's some intrinsic cadence to the observations that has a 24-hour period, because we have to wait for the sun to go behind the Earth to make these measurements. So this is the beat frequency. The dashed lines are the beat frequencies. So if the frequencies add versus the frequencies subtract, typical RR Lyrae periods are less than a day. So the frequency is higher than 1 day. So F-1 and F+1 are the two dashed lines that you're seeing here, but in period space instead of frequency space. And most stars land either on the 1-to-1 line, but in some cases, either us or Pan-STARRS-1 measured a beat frequency instead of the true frequency. We have better sampling. We have somewhat better sampling than PS1. We have much better photometric precision. So we think these are instances where Pan-STARRS measured the beat frequency, and that's why they're not on the 1-to-1 line. There are two stars that are off any of these curves, so we're not sure what happened there. Okay, so these are periods compared between one survey and another. This is our photometric precision compared to, these are, every blue dot is an object in NGVS, and we have multiple measurements of them in the G filter, U filter, I filter, and Z filter. This is just showing the G filter, looking at the 1 sigma RMS of the measurements. Most objects are non-variable, so the 1 sigma we measure is really a measure of our photometric precision. This is it for us, the dashed line, but there are two major RR Lyrae surveys covering larger area than we do. One of them is DES, the Dark Energy Survey, and you can see that their single epoch precision in the G band is quite a bit worse than ours. And single epoch precision is important, of course, for measuring variable objects. They have a comparable number of measurements to what we have. They don't have the U band, I believe, but they have multiple filters. The HIT survey is done in a single filter, and they have worse single epoch precision than DES. And just roughly speaking, if we make the comparison at sigma of 0.05 at 5% precision, our NGVS data go 1.7 magnitudes deeper than Caitlin Stringer's DES results, and 2.3 mag deeper than Gustavo Medina's HITS paper from 2018. Now, I want to compare, I want to show our stars here. These are NGVS stars, the 200 or so stars that we found. This pizza slice, one of the crust of the pizza slice shows you right ascension, and the radial axis of the pizza slice shows you the distance of the star. You see a cluster of stars around 40 kiloparsecs. That's the Sagittarius stream in the foreground of the Virgo cluster. Every red circle is an RR Lyrae that we found. The starred symbols are the 6 most distant ones, and you can see the most distant one is somewhat beyond 300 kpc. Just to give you a sense, there's very little known about the Milky Way in terms of its halo, very little known about the Milky Way halo beyond about 100 kpc. There's very little kinematical information. So this is really probing a regime of the Milky Way halo that hasn't been studied very well to date. We are measuring spectra of stars. We are focusing on about 100 to 200, measuring radial velocities, spectra of stars with Keck and ESI. Very hard work. We can't go beyond 200. Stars are too faint. And what we have just from the photometric data alone, is we have a density profile from our data. That's the red dashed line. Those are our data points from NGVS. Density, number of stars per cubic kiloparsec, as a function of distance from the galactic center, a logarithmic scale on the x-axis, logarithmic scale on the y-axis, and the best fit slope is about minus 3.4 over here. Now, I'm also showing you data, or I'm showing you fits from the HIT survey. That's the dotted line. They fit out to a little beyond 200 kpc. They don't trust their data beyond that. DES fits out to 100 kpc. They don't trust their data beyond that. When I say they don't trust their data, I think one of the main things the DES worries about is quasar contamination. That is, objects with aperiodic variation that have been misidentified as RR Lyrae. We are finding some of these misidentified RR Lyrae when we take spectra. We haven't found a single one in NGVS yet, but we're finding them in other surveys. They got high scores in terms of light curve fitting, but when you don't have enough measurements, quasars can contaminate RR Lyrae samples, distant quasars. Okay. I'll skip over this graph. Well, this is maybe I'll say a word about it. This is something derived from the Bailey diagram. A Bailey diagram is a plot of period on one axis, period on the x-axis, log of period on the x-axis versus amplitude. And people have seen from known RR Lyrae in globular clusters that the position in that diagram is sort of a proxy for metallicity. So the x-axis you can think of as a proxy for metallicity. Further to the right are metal poor stars. That's what that dashed line shows. And the solid line shows somewhat more metal rich stars. The y-axis here, so the x-axis is a proxy for metallicity, even though it's delta log p in the Bailey diagram. On the y-axis is distance of the RR Lyrae from the center of the Milky Way. You can see the Sagittarius stream here, the distance of about 40 kiloparsec. This is now a linear scale of our galactic center, distance from the galactic center. And at 40 kiloparsec, you see this concentration of relatively metal-rich stars that are the Sagittarius stream. But as you go further out, you have mostly or entirely metal-poor stars. So beyond about 200 kiloparsecs, there are very few metal-rich stars. And again, this is a very crude proxy. The x-axis is a very crude proxy for metallicity. This is the work of Yuting Feng. And the spectroscopy we're doing is in conjunction with Emily Cunningham, whose picture you saw earlier. All right, I'm going to switch gears in the remaining time. By my calculation, I have something like another 12 minutes. Guy, is that right?
Wow, you calculated that closely. Yes, that's good. Okay,
I'll say a little bit about Andromeda's disk and the M33 disk, and then that'll save time for questions afterwards. Okay, I have to show you this. I'm going to actually stop sharing my screen for a moment because I want to optimize it for video. Just a moment, please. I realized I hadn't optimized for video when I shared my screen, but here we go. You should see my screen again, and I'm going to play this video. This is a zoom in. You're seeing the arc of the Milky Way in this on the sky. And you're seeing Andromeda there, where my cursor is pointing, 2.5 million light years away. But as we zoom in, you see more details of the Andromeda galaxy and its satellite. And we're going to keep zooming until we can see a lot of detail in the disk of Andromeda, a lot of detail. I mean, individual stars. And these individual stars in the disk of Andromeda, this image that you're seeing here, we are panning across slowly now. We're no longer zooming in. These stars are from a 6-band photometric survey, imaging survey of Andromeda's disk. This is the largest mosaic image ever obtained with Hubble. It's a mosaic of how many fields? Let me think about this. 414 Hubble fields stitched together into a contiguous mosaic, over 400 fields. So this was a multi-cycle treasury program carried out, started at the same time that the Candles survey was started. And you're seeing a portion of that. The colors, of course, represent different temperatures of stars. You can see a few patches of dust here. There's been some wonderful papers written about the dust layer in Andromeda's disk. We are using it to study, to isolate stars and measure their spectra. So our UCSC team has been part of the PHAT team, Panchromatic Hubble Andromeda Treasury, what PHAT stands for. And it's now been extended to the southern part of Andromeda's disk and also to Triangulum. Okay. I want to say a little bit about dynamical heating of these two disks in the remaining time, M31 and M33. I want to show you this plot from Claire Dorman's PhD thesis. And this is a strange-looking map of Andromeda. Well, on the lower right is a Herschel map of the dust in Andromeda. And on the same scale, you can see the PHAT survey. This is the center of Andromeda, is this X. The PHAT survey covered the sort of upper left part, what's called the northeastern disk of Andromeda. It covered not all of the disk. It avoided the most reddened dust lanes in this edge. This edge of Andromeda in the upper right edge of the disk is the near edge. So that part has the most prominent dust lanes. PHAT avoided that. And what you're seeing here are the stars in Andromeda divided into three groups. Upper left are young stars, or short-lived main sequence stars, massive main sequence stars. They live for well under a billion years, a few 100 million years. Then you see intermediate age AGB stars. These are stars above the tip of the red giant branch that have masses that are a few times the mass of the sun, 2 to 3 times the mass of the sun. They live for a few billion years. And then in the lower left, you see long-lived RGB stars. These are old. They have lifetimes that go up to 10 billion years. So the typical star, Andromeda, has been forming stars continuously at a steady rate over its lifetime. The typical star should have a lifetime of about 5 billion years. Okay, so what you see is that, of course, we've taken every dot is a star for which we obtained a spectrum. And you can see we have spectra for many more old stars than we do young stars. But the color coding of each dot is important here. The color coding of each dot is according to the standard deviation of line of sight velocity of its neighbors. So around each star, we draw a small circle, and we say, we measure the standard deviation of line of sight velocities of the neighbors of that star. If that line of sight velocity dispersion is small, if it's 20 or 30, it gets a dark color. If it's large, if it's more than 100, if it's 150, it gets a bright color, it gets a bright orange. And you can see there's a very stark difference in colors when you go from young to intermediate age to old. So again, in the color magnitude diagram, this is our crude definition of old for RGB stars. These are 475W is a B band minus I band against I band luminosity. This is a Hertzsprung-Russell diagram where you can treat apparent magnitude as luminosity because these stars are at a common distance, Andromeda's distance. On the left, you see main sequence stars. The main sequence looks vertical here because these stars are so hot that in this baseline, V minus I, we are no longer sensitive to temperature. We're on the Rayleigh-Jeans side of the blackbody function. So main sequence stars, massive main sequence stars show up as this vertical streak in the far left. We see RGB stars. You see the tip of the red giant branch here. This is the full CMD with Hubble. Most stars are too faint for us to get spectra, so we look at stars that are brighter than about 24th in the I band. But our stars are actually that's this inset is brighter than 24th, but our spectroscopic targets, for the most part, brighter than 23rd. Most are brighter than 22nd, actually. So, and we take the intermediate age AGB stars, these are the stars above the tip of the red giant branch, and divide that into a luminous and less luminous sample. The luminous stars are somewhat less long-lived than the less luminous. The faint AGB is somewhat longer-lived than the bright AGB. Here are histograms of velocity dispersion. Mind you, this is a disk component, and it has, for the RGB stars, it all looks like a thick disk. It has a very high dispersion, about 100 kilometers per second, whereas the young stars have a dispersion of 20 to 25 kilometers per second, line of sight velocity dispersion. This is another way of looking at the data. Line of sight, or this is the mean, line of sight velocity dispersion as a function of age. And the filled points are 4 age bins in Andromeda, and depending on what you assume for its star formation history, if you assume a constant star formation rate, then you get these ages. But if you assume a declining star formation rate, then of course the average age of the stars is older in the old and intermediate age populations. Either way, you get a graph that is very different from the Milky Way. The Milky Way data points are much lower and a shallower slope. So dynamical heating seems to be much more prevalent in Andromeda, and whatever the source, much more prevalent, and also seems to have a steeper slope. So the rate of heating seems to be higher. Okay, not just the cumulative amount of heating. This is Claire Dorman's PhD thesis from 2015. And Amanda Quirk continued this work, and she looked at asymmetric drift. This is now the rotation speed. Now the color coding is by line of sight velocity. You can see a clear rotation pattern in the disk, but the rotation pattern is most extreme in young stars, least extreme. The color contrast is much less for RGB stars. So she sees a very clear asymmetric drift. This is measuring the stellar rotation relative to, we are using H1 as a proxy for circular velocity as a function of age. And again, you can see this, the colors now represent asymmetric drift, and the colors are much brighter for old stars than it is for young stars. Old or long-lived stars much higher than for young or short-lived stars. And this is the work of Amanda Quirk. She's a postdoc at Columbia University now. All right, I'm going to skip this. I'm actually going to skip this in the interest of time. And in my last couple of minutes, I want to talk about some work we're doing in M32 and M33. So this is actually a pattern of masks that we were observing at Keck this past weekend. And this is work that is, we are using to study M32. It's very nice. You can really see M32 and M31 as two separate peaks in velocity space. Those are those two peaks. If you march close to M32, you lose most of the M31 disk and you get the M32 disk. And if you march away from M32, you lose most of the M32 peak and you get the M31 peak. We're also getting the halo of M31 here. So this is based on some 2019 masks. In 2022 and 2023, we really beefed up the amount of coverage here. So we expect these graphs to get much less noisy moving forward. And what we're trying to do is use CMD information, sky position, velocity, to measure the proper motion between M32 and M31's disk. And this is the work that Mark Fardell is leading from Space Telescope. This is what we have by way of a velocity map of Andromeda so far. You can see we've gone from just covering the northeastern part of the disk to also covering the southwestern part of the disk. This little hole here is M32. We can't get too close to its center. We can't do resolved stellar populations too close in. And this is something that we are also exploring, the stellar disk of M33. I haven't shown you a picture, but the stellar disk of M33, young stars are very well behaved. They move just like the hydrogen. This is the velocity offset between the star and the H1. But if you look at old stars, they're not very well fit by a single Gaussian. This is a single Gaussian fit to the velocity distribution of velocity offset between stars and the H1 disk. This is for long-lived RGB stars. Young stars, a single Gaussian is a great fit. Old stars is not a great fit. A two-component fit is much better. And so we've detected a dynamically hot component in M33. It seems to be located in the central region of the galaxy. It is, it's got a high dispersion and it accounts for about 15% of the population. And this is, whereas the young stars, there is no dynamically hot component. This is the work of Amanda Quirk and Carrie Gilbert, the two papers that they published in early 2022. Lara Cullinan is continuing this work to intermediate age stars. And again, she sees a hint of a dynamically hot component even in intermediate age stars. And this is Lara is a JHU postdoc who's actually visiting me in Santa Cruz right now. And this is a paper that's just been accepted for publication. I should change that, submitted to in press. It just got accepted. Okay, I know clear out of time. Shall I stop here and take questions, Guy? Or I have 3 slides, I think, to talk about other work as teasers. What should I do?
Tease us.
Tease you. Okay. So I'm going to tease you by talking about galaxies that are a little further away. This is a galaxy called NGC 4449, 3.5 megaparsecs away. It's a dwarf galaxy that's in the process of cannibalizing something even smaller. And that's the something even smaller is this streak over here. This was discovered independently by 2 groups. We are not part of the discovery, but we put a DEIMOS mask down and tried to measure velocities. Now, if you look in this section where we have HST imaging, you can see that things that look like stars in the ground-based image are actually surface brightness fluctuations. They are collections of stars. They're not individual stars. They're SBFs. SBFs are famous. Surface brightness fluctuations can be used to measure distances to galaxies. Here, we are using them as co-addition points, places where nature has added the light of stars for us. If we target them, we can get the light of multiple stars in one set, and we use that to measure a spectrum. And by co-adding, we can measure the calcium triplet, we can measure velocities. We are co-adding blends, essentially, in the case of that galaxy. In this case, because we had HST imaging, we're co-adding the spectra of individual stars, not blends. But individual stars and blends doesn't matter if we're trying to get a mean velocity for a particular region. We can also, with some modeling, we can also try to infer the metallicity. So this is something that we've done in a few galaxies, M81, in NGC 253, and in CEN-A. We also find rare populations in M31, M33. You're all familiar with carbon stars. We are finding this very odd variety of stars that this CN feature, this is very sharp W-shaped feature, we're seeing a hint of that in some stars, while they have otherwise perfectly normal spectra with calcium triplet and TIO. That's what's marked by the blue bands. Blue shows TIO on the left, calcium triplet on the right. So these are stars that have oxygen-rich features and carbon-rich features. And my student, Doug Grionfillo, and I are writing a couple of papers on these. This work the carbon star work was done by a PhD student, Katie Hamron, and the work on weak CN stars has been the work of several undergraduates and high school students. Okay. So with that, I put up my summary. I talked briefly about the accretion history and chemical enrichment and extent of the Milky Way halo through the lenses of the HALO7D and NGVS surveys. I didn't talk about BP3M, but it's using HST and Gaia in conjunction to measure proper motions. This is what Kevin McKinnon is leading. I said a little bit about the stellar disk dynamics of M31 through the lenses of the SPLASH and other surveys, and M33 stellar disk dynamics through the lenses of TREX and PHATTER. These are Keck and HST surveys. And with that, I'll stop and take questions. Thank you very much.
Question? Yeah. Yeah, nice talk. How easy or difficult is it to explore, let's say, the halo stars of Andromeda? I mean, especially the ones towards along our line of sight. I mean, you're reaching out with RR Lyrae in up to roughly half of the distance to Andromeda, right?
Yeah, that's a question I get asked a lot. And have we found stars in? You're saying when we look towards Andromeda, have we found stars that are, say, halfway between us and Andromeda? We haven't found that yet. The main work we've done in Andromeda has been to expand away from the center. That is to march away from the center as projected on the sky. And that's how we've mapped out its halo, not by mapping it along its distance along the line of sight, but really perpendicular to a line of sight. We've mapped out the Andromeda halo. Now, there isn't, we don't have access to, or I don't think there is, a very good wide field time domain survey in the foreground of Andromeda. Partly, it's a huge field of view. Andromeda's halo, just to give you an idea, is how far out do we go? We go out to about 200 kiloparsecs in projection. That's 25 degrees in diameter. Andromeda's about the size, Andromeda's diameter of Andromeda's halo is 25 degrees. That's comparable to the size of the Big Dipper. It's huge. And we don't have any large-scale time domain survey over that we would use to look for distant RR Lyrae. So I bet there are stars in the direction of Andromeda that are halfway, but we haven't found them.
Okay, thanks. I should mention, if you're on Zoom and you want to ask a question, just unmute and fire away.
Okay.
But I have a question in the meantime, which is, I think RR Lyrae stars are supposed to have a kind of a youth limit, right? If you're an RR Lyrae star, you have to be older than some number. So firstly, what is that number? And secondly, can you use that for scientific conclusions?
That's a great question, Guy. I mean, yes, they have to be on the horizontal branch. They have to be a low mass star on the horizontal branch. There is absolutely a youth limit. We don't expect to see young stars in the halo, so I don't think that's introducing a terrible bias into studies of the halo. We do expect to see the RGB stars and, let's say, even main sequence stars that are associated with these RR Lyrae. The RR Lyrae are on the horizontal branch. There is indeed bias against youth if one against stellar youth. That is, if we are using RR Lyrae to probe the halo. Metallicity wise, there's also somewhat of a bias. We don't expect very metal rich stars to populate that part of the horizontal branch that extends into the instability strip. You know, if you have a metal rich population, they'll form a red clump. They won't intersect the instability strip, and where the horizontal branch intersects the instability strip is where we get RR Lyrae. So there's those two kinds of biases when using RR Lyrae.
Thank you. What else? Right, I'll give you 5 more seconds.
I have one question.
There's one.
Do you have, what's the best place to learn about this subpixel imaging and detection techniques? And do you have some data like we could work with, students could use as a way of trying out these
So the people, I'll put some, or I'll let me put some names in the chat.
Okay, great.
So Jay Anderson has been the leader of this, but he's worked with Bellini. I'm trying to remember, Andrea Bellini, I think is the name. They've written papers. They've also written technical documents. What they've done is they've measured, they've taken images of 47 Tuc over and over and over again with different rotations, and they've used that to measure positions with very high precision. They have this method called the effective PSF, which is where the main focus is to measure the precise position for the star. It's just through PSF fitting that they're fitting positions, of course. They really have. Jay started this work when he was a PhD student with Ivan King at UC Berkeley, but he's really been the leader of this effort. Those are two names that come to mind. The other thing that I'll put in the chat is this thing called HST Promo, stands for HST proper motions. This is, of course, measuring positions precisely with HST is key for that project. And that's a loose collaboration involving many people, including us, that Roland leads. Roland Vandemar, whose name I'll put in the chat as well.
Thanks.
You're welcome to tell these people that I put you on to them. They are really the world leaders in this work.
That's not with the outreach. Yeah. Can you describe Shadow a Scientist?
Oh, I would love that. Let me, if Jamika, if you wouldn't mind taking a moment to introduce yourself, and then I'll describe the program happily.
Absolutely, it's my pleasure. Aloha nui kako. My name is Jamika Marshall, and I am the coordinator for the Shadow the Scientist initiative. I am located here on the Big Island of Hawaii, where many of our astronomy observations take place. As Roger was saying, actually, if I can just share my screen really quickly, we have the Shadow the Scientist program, which is a part of CREST, the Creating Equity and Esteem. And with Shadow the Scientist, we offer real-time interactions with scientists conducting authentic and uncurated research across a range of fields. Of course, astronomy was the first field, but we're bringing in engineering and biology, which is really, really exciting. Our shadow sessions not only encourage participation in research practices, but it also provides opportunities for our participants to engage in critical thinking in the context of research. I'll stop my share here. I will drop a link to our webpage in the chat, as well as our YouTube channel. As Roger was just saying, he was just here. We had an event over the weekend together. It was always so wonderful to work with Roger in person, observing on Keck over the weekend. And we have a few of those videos on our YouTube channel, as well as our first session with the Deputy Director and Chief Scientist of Keck Observatory, Dr. John O'Mara. So please feel free to check those out. You can email me and Roger for any other questions you have about the Shadow the Scientist initiative. Mahalo nui loa.
Shamika, thank you very much. So in fact, this weekend we're offering 2 shadow sessions on Saturday night. We're using, there's a group of us who are using the Lick 3-meter, Shane 3-meter telescope. And so if some of you in the audience, maybe many of you in the audience are observational astronomers and you use telescopes for your research, we would love to shadow you. And we want to make it as painless as possible. If you tell us a time and date and give us just a non-technical paragraph about what science you're going to be doing, what instruments you're going to be using, like literally a few sentences for that. Jamika and I will connect with you, and we would advertise the session to students around the world. We literally have students from around the world to connect. We have students from Africa, from South Asia, strong focus on the global South. We've had students from Colombia, from Mexico connect to these sessions. That's what I have. It's trying to demystify professions for young people. That's really what it's about.
Right. That's fabulous. Last minute questions?
I have 2 questions.
Yeah, 2 questions.
Related, and hopefully that's. First, would it be possible to get the links that have been shared in chat sent to like the physics? Or posted on Slack somewhere.
I'll stuff it on the Slack for sure.
And then the other question was, for the shadow scientists, are you looking specifically for like professors, or are grad students eligible to volunteer or something like that as well?
I think I heard that question, and it's open to anyone who's operating, who's doing research, or really anyone who's engaging in critical thinking in that process. In astronomy, of course, very often it's grad students leading observing runs. Sometimes there are undergrads involved. That's what it's going to be this weekend for us. It's actually 2 grad students and 1 undergrad who will be leading the observing run. Absolutely, it's open to anyone. It's a free program. We offer it for free to students around the world. We would, what we ask of the host is your patience as a bunch of eavesdroppers connect to your Zoom call while you're operating the telescope. If you want to designate someone as who's not running the experiment that night, as someone who'd act as a moderator and explain what you're doing, that would be fine too. We could actually pay for their time as well. If it's a grad student doing the moderation, we could pay for their time.
Okay. All right, let's thank Roger one more time.
Thank you very much, Guy. Thank you for having me.
Yeah, you're very welcome, and thanks for giving the talk, and have a wonderful day, and thank you so much.
Bye everyone.
Bye.
Bye, Jamika.